It's my first talk in Moscow, which is not really in Moscow, but kind of in Moscow, like virtually in Moscow. So thank you for this invitation. And I will start with the motivation. Then I'll present some results. Not only those I announced in the abstract, and then I'll actually go to the proof of main results. So let me start with a very basic question. Is a geometric object uniquely determined by its group of symmetries? Well, let me take probably the easiest geometric object. It's just a finite set. And let me take as its group of symmetries the group of all bijective maps from S to S. So this is a well-known symmetric group. It is very well known that if we have two finite sets, S and S prime, and if the group of symmetries are isomorphic, then there is a bijective map from one set to another. So basically it says that group of symmetries of a finite set determines the set S in the category of finite sets, but you can actually remove in the category of finite sets. So a finite set is determined by its group of symmetries. Of course, we would like to have this statement for some more interesting geometric objects, not just for finite sets with discrete topology. So I passed to Erlangen program. You probably know this guy, or kind of know, so maybe you saw this picture. So his name is Felix Klein. And in a sense, I have to talk about Erlangen program because Erlangen is not that far from Vienna, just two hours by train. So it's kind of good thing to talk about Erlangen. So this guy in 1872 proposed that the group theory, a branch of mathematics that uses algebraic methods to abstract the idea of symmetry, was the most useful way of organizing geometrical knowledge. One can translate his words into a modern language as to study geometrical objects via their transformation groups. Of course, it depends on the object. You can take as the transformations, diffeomorphisms, isometries, automorphisms, variational transformations, and so on. I forgot to add at the beginning that this should be considered as a kind of friendly talk, so you are very welcome to interrupt me at any moment if you have a question. But nevertheless, let me get back to Erlangen program. So this approach was very fruitful in many areas of mathematics to study manifolds, for example, to study manifolds via their diffeomorphism groups. Here I would like to point out a result which is due to Philip Kevich. Let M and N be smooth manifolds without boundary, and let their groups of diffeomorphisms are isomorphic as abstract groups. Then there exists a diffeomorphism from one manifold to another. So that's basically what we want. We have a similar situation as for finite sets, right? So a manifold, smooth manifold without boundary is determined by its group of diffeomorphisms in the category of smooth manifolds without boundary.
And question, and does this theorem claim that any isomorphism between diffeomorphism group comes as a pullback from some diffeomorphism of variety?
Exactly. I didn't write here, but it does exactly what you said. So he proved more than I said here. He proved also what you said. Exactly. So the isomorphism between diffeomorphism groups comes from this diffeomorphism between manifolds. So since we don't do here differential geometry, we would like to have this kind of statement, but for other geometrical objects, for algebraic objects. So let me come back to my question again. Is a geometric object uniquely determined by its group of symmetries? Of course, as a geometric object, we take algebraic variety. There are at least two natural possibilities for the group of symmetries. One is the group of regular automorphisms of algebraic variety X, and the other is the group of birational transformations or birational automorphisms of algebraic variety X. Of course, the group of birational transformations is much, much bigger than the group of regular automorphisms. Hence, a bigger group should contain much more information about the variety. So it should be much easier to characterize your variety with the help of this huge group, the group of birational transformations. So let's try it at the beginning. Here is a very nice result, which goes back to Sashkanta and Junichi. Let X be an n-dimensional quasi-projective variety, where n is bigger or equal than 2. If beer X is isomorphic to beer Pn, then X is rational. And rational means it's birational equivalent to Pn. So these two guys actually proved much more. They prove that if X is a variety of dimension n, and there exists an injective morphism, so a homomorphism of groups, from SLN plus 1z into beer X, then X is rational. Then X is birational equivalent to Pn. So now, of course, since beer Pn contains a copy of SLN plus 1z, then beer X also contains a copy of SLN plus 1z. And by this statement, we get that X is rational, that X is birational equivalent to Pn. Actually, Kanta and Shi proved much more, or at least more than I state here. They proved this statement not only for the homomorphism from SLN plus 1z, but from a finite, but for any homomorphism from a finite index subgroup from SLN plus 1z to beer X. You probably know that SLN plus...
One more question. Let us assume that n plus 1 is even.
No. Yes, okay.
Then this subgroup SLN plus 1z contains minus unit, right? This is the central element. And it acts trivially on the projective space.
Yes.
So we don't have embedding, we don't have injective morphism.
This is true. And no, wait. So I had here an assumption. You mean, okay, so I see what you mean. You mean that is, okay. Anyhow, so what Kanta and Shi proved, they proved the statement for any gamma, which is a finite index subgroup is in SLN plus 1z. Okay, so this covers also your question.
No, the question is, how do you, in the rational case, how do you invert the group SLN plus 1z into the Cremona group?
Into BPN, you mean?
Yes, into BPN.
Okay, so so let me repeat what I said. So the statement is proved not only for SLN plus 1z, but also for any finite index subgroup in SLN plus 1z. So maybe I have to be a bit more accurate and put here not SLN plus 1z, but any finite index subgroup in SLN plus 1z.
No,
then
but
of course,
if the quotient group act, it doesn't. It's not a finite index subgroup. I mean that you have action of the quotient. You take the subgroup modulus central.
Yes, but okay. So I don't have to go too much into the details, but you can. What you can do, you can find a finite index subgroup in SLN plus 1Z, which does not intersect your group, any finite subgroup.
Okay.
So this is possible. It's actually kind of clear. So you take a projection from SLN plus 1Z to SLN plus 1Z Z quotient by MZ. Take the kernel. The kernel will be a finite index subgroup, and it will not intersect. If you will take high enough M, it will not intersect any finite subgroup.
Okay, maybe modulo this trick, it should be clear. Okay.
Okay. So basically, this theorem says that Pn is uniquely determined up to a birational equivalence among n-dimensional varieties by its group of birational transformations. But first of all, it determines it only among n-dimensional varieties or of varieties of dimension less or equal than n. And secondly, if we take two rational varieties, then they have the same group of birational transformations. So basically, you cannot distinguish two non-isomorphic rational varieties by their groups of birational transformations. Therefore, if we want to determine the variety up to an isomorphism, we have to go to regular automorphisms. But here we also have a problem. Most toric projective varieties have automorphism group isomorphic to algebraic torus. Hence, projective toric variety cannot be determined by its automorphism group. So we tried the group of birational transformations, it didn't work. Now we tried the group of regular automorphisms, but for projective varieties, and it also didn't work. Well, let's try now. So the last step, so to say, affine varieties. And this is a little bit more natural to try this because the automorphism group of affine variety can be much, much bigger than the automorphism group of projective variety. So the bigger group contains more information. It should be easier, or at least possible, hopefully, for affine varieties. So my question, which I ask now, is the following. Let X be an affine irreducible variety with the rich automorphism group, and Y be any irreducible variety such that there is an isomorphism from out X to out Y. How similar X and Y are? Can we say that they have the same dimension, or maybe even that they are isomorphic, or at least something? First, you can ask me what it means to be rich. Let me consider probably interesting, but the most basic example. It's the example of the affine plane. So automorphism group of A2 contains two subgroups. One is a subgroup of shears along one coordinate, and another one is a subgroup of shears along another coordinate. Both these groups are isomorphic as a groups to the polynomial ring in one variable. So both of them are quite big, infinite dimensional. And our A2 contains even a free product of these groups. So it's fair enough to call out of A2 a big, a rich group. Now let me introduce a notion of a spherical variety. So why spherical variety is of interest for us? Because the automorphism group of a spherical variety, of any affine spherical variety, is rich, except one case, except if this variety is an algebraic torus. So algebraic torus is actually a unique spherical, affine spherical variety which does not admit a GA action. Anyhow, let me start with the definition. Let G be a reductive group and B be its Borel subgroup. An affine normal G variety X is called spherical if B acts on X with an open orbit. So for example, if you go to dimension 2, then all affine spherical surfaces are toric except 2. There are only 2 non-toric spherical surfaces, namely SL2 quotient by torus or SL2 quotient by the normalizer of the torus. And let me go back to my remark that T is a very specific spherical variety. You see, if you take any affine spherical variety which is different from algebraic torus, then it admits a G action. And once the dimension of the variety is bigger than 1 and it admits a G action, then it admits tons of G actions because you can take replicas. And this makes your group quite big, well, infinite dimensional at least. So that's why spherical varieties, as I said, are of interest for us. And also because they are well studied and they admit a very nice combinatoric. Now, I would like to introduce the notion of an isomorphism that preserves algebraic subgroups. An isomorphism phi from out X to out Y, X and Y are affine. So from now on, all my varieties are affine. So an isomorphism phi that sends an algebraic subgroup to an algebraic subgroup, and restriction of phi to an algebraic subgroup induces an isomorphism of algebraic groups, is called an isomorphism that preserves algebraic subgroups. Now let me introduce a weight monoid. Well, if X is a spherical G variety, this means a Gx on X. And this induces a G action on the ring of regular functions O of X. So in the other words, O of X is a G module. So if X is spherical, then actually O of X is multiplicity-free G module. That means the multiplicity of every irreducible module in O of X is at most 1. And by the weight monoid of X, we mean the set of all highest weights of the G module O of X. Now, characterization of spherical varieties. So this is the statement which you already have seen in one of your talks, I think by Victoria Borovic. But I nevertheless state it and will give some extra remarks on this result. Let X be a spherical affine variety different from algebraic torus, and Y be an affine irreducible normal variety. If there is an isomorphism from out Y to out X that preserves algebraic subgroups, then Y is spherical and X and Y have the same weight monoids. So you have to exclude here algebraic torus because for algebraic torus is simply not true. And why it's not true for algebraic torus? So the reason is that algebraic torus does not admit a GA action. This is basically the reason. Corollary.
No, but for torus, there is a counterexample. So the statement is wrong for torus.
Yes, the statement is wrong, and I will give you a counterexample just in 1 minute. If X is toric, then Y is isomorphic to X. If X and Y both are smooth, then Y is isomorphic again to X. So in these cases, toric or smooth spherical variety is determined uniquely by its group of automorphisms. So again, if X is spherical, then Y is spherical. And if you assume that both are horospherical, then Y is also isomorphic to X. But in general, for a given X, there are finitely many spherical varieties, Y1 and so on, YL, such that out Yj is isomorphic to out X. I should say that there are most finite. We don't know. It's most probably there is only one. But what we can prove that there are most finitely many. I mean, this is just a consequence of the result by Ivan Lossio, that there are finitely many. So it would be nice, of course, to prove that there is only one. But so far, we could not do it. So example, the case of algebraic torus. Let T be an algebraic torus, and let C be a smooth affine curve. If C has a trivial automorphism group and no invertible global functions, then there is an isomorphism, actually a natural isomorphism, from out T to out C times T that preserves algebraic subgroups. You see, if you would take any other spherical variety, which is different from T, then this would not be possible. The reason is if you put instead of T here X, then X admits a G action. Then you can take this G action on X and take a replica with some regular function on C. And it will induce another G action which already involves C inside of this G action. So this isomorphism would not be possible if you put here any other spherical variety different from algebraic torus. But for algebraic torus, you can do it. And moreover, it's actually important to assume that there are no invertible global functions. If there are invertible global functions, this trick wouldn't work. But if there are no invertible regular functions, it works. You can look it up in the paper. I don't spend more time on this, but for algebraic torus, it really doesn't work. But what works for algebraic torus is that algebraic torus is determined by its group of automorphisms in the category of varieties of dimension less or equal than dimension of torus. So if you assume the same dimension, then of course it works. But you cannot bound the dimension. So that's the point. Non-spherical case. So I would like to tell you one example, it's namely Danilevsky surface. Let me define dP as a surface in A3 defined by equation xy equal p of z. And let me assume that p has no multiple roots. This means that dP is smooth. Then for two generic polynomials p and q, there is an isomorphism phi from out dP to out dq of abstract groups that maps isomorphically each algebraic subgroup in out dP to an algebraic subgroup in out dq. Moreover, the restriction of phi to each algebraic subgroup in out dP induces an isomorphism of algebraic groups. So this phi is an abstract isomorphism that preserves algebraic subgroups. You see, the statement we had for spherical varieties fails if we go to Danilevsky surfaces. Nevertheless, here is a result which will appear next week on Archive. Let X be an affine irreducible variety and assume that out X is isomorphic to out dP as an int group. Then X is isomorphic to dP as a variety. So if you put extra structure on the automorphism group, namely int group structure, then this makes this object, the automorphism group, very rigid, much more rigid than just isomorphism that preserves algebraic groups. And in this case, we can really determine dP by its automorphism group. Note that we don't need any normality on X here, like we needed in the case of spherical varieties. Actually, in this paper, I prove more. I have to do it like this now. So in this paper, I prove more. If Y is an affine irreducible surface endowed with a hyperbolic GM action, and our X is isomorphic to our Y as an abstract group, just as an abstract group, then Y is an again affine surface endowed with a hyperbolic GM action. So it says that hyperbolicity is preserved. Note that it's not
typo.
Sorry?
Shouldn't there be X instead of Y somewhere? Well,
Yes. So you are right. Here has to be X. Oops. So here at this point has to be X. So I'm sorry. So
and I wanted. Oh, okay.
Yes. Yes.
I wanted to ask.
yes.
Is this true that these Danilevsky surfaces are not isomorphic for different P and Q?
This is a good question. They are not. They are not. So dp and dq are isomorphic if and only if there exists an isomorphism from CZ to CZ, algebra isomorphism, which sends p to q. So for example, if p and q have different degrees, then dp is never isomorphic to dq.
Oh, so if and only if P is a somewhat linear transformation of Q.
So yes, if and only if by changing the coordinate z, you can send p to q.
I get it. Yes, thank you.
I don't understand. Well, the example with the next services, you say that for any polynomials p and q, there is an isomorphism.
Yes.
But by the proposition, so for different Danilevsky surfaces, you have the same automorphism group. Oh.
No. Like here in this example, I say that there is an isomorphism from our dp to our dq that preserves algebraic subgroups, but it's not an in-group isomorphism.
Okay.
And in proposition, in these first two lines, I require the in-group isomorphism. So if you have an in-group isomorphism, then actually you have that the Danilevsky surface is determined by its group of automorphisms.
So all these isomorphisms in the example are not in the group isomorphisms.
It's not an in-group isomorphism. I mean, a priori, we didn't know it, right? We didn't know it. It's not clear why it's not, or it was not clear why it's not an in-group isomorphism. But after some time, we understood that it's not. Yes. So, and in this last three lines of the proposition, we assume only an abstract group isomorphism. So this hyperbolicity is characterized by an abstract group isomorphism. And moreover, I should say that if you like to prove something like this for not hyperbolic, but parabolic or elliptic GM surfaces, then it fails. Then it fails. Okay, let me go further. Very rough idea of the proof of spherical theorem. Let X be an affine spherical G variety. An important subgroup H in our X is called a generalized root subgroup with respect to a Borel subgroup B. If H is commutative and every one-dimensional subgroup of H is normalized by B. So the weight of all the one-dimensional subgroups of a generalized root subgroups are the same. And this weight we call the weight of the generalized root subgroup. So this is just a generalization of the standard notion of a root subgroup, or if you like, the Mazur root. So here is a proposition. Let Y be an irreducible normal affine G variety. then the following statements are equivalent. Y is G-spherical, and there exists a constant C such that dimension of H is less or equal than C for each generalized root subgroup H in out Y. Actually, this constant C can be given precisely. For example, you can take a dimension of X or even dimension of X minus 1. It can be given even more precisely, but I don't want to do it now. And we also didn't do it in the paper because we didn't need it. But as I said, this constant can be given quite precisely. So this proposition tells you that if you have an isomorphism from out X to out Y that preserves algebraic subgroups, and X is G-spherical, then Y is again G-spherical. This is the first part of the proof of the spherical theorem we have. And this is actually the elementary part. So the difficult part is really to prove that two spherical varieties X and Y have the same weight monoid. So this is a tough part. You have to go to affine, how is it called? Asymptotic cons and really play some involved combinatorics. But of course, I don't want to do it, and it's not clever to do it in the talk. So I skip that and go to the real question. And the real question is, well, the real question appeared after we could do the previous result, of course. But the real question is, if out X and out Y are isomorphic only as abstract groups, what can we say about similarity of X and Y? But first, I have to tell you a little bit about int groups. Probably all of you know the definition of an int group, so I'll not do it. I'll just give you an example of the int group structure on AN and similar structure we have for any affine variety. If we define out A and D as a group of all automorphisms of AN, such that the degree of F and degree of the inverse of F is less or equal than D, then this out A and D is an affine variety. It has a natural structure of an affine variety. And of course, out AN is a union of this out A and D. So out AN is not an affine variety itself, but it's a union of affine varieties with certain properties, actually. And similar trick can be done for any affine variety. So this basically brings us to the int group structure. Now, what is the main issue which we face for this abstract group isomorphism from out X to out Y? So X and Y are affine here as always, and phi is an isomorphism of abstract groups. Assume X is toric. It is not clear if phi sends algebraic subgroup to an algebraic subgroup. It's not clear if phi sends algebraic subtorus to an algebraic subtorus. Moreover, it's not even clear if out Y contains a single algebraic subgroup of positive dimension. It's not clear, and it was not clear until quite recent time. Here is an example. There exists an affine surface S and an isomorphism psi from out S to itself, such that for any algebraic subgroup H in out S, its image is not an algebraic subgroup in out S. Moreover, the image of each algebraic subgroup is dense in out S. So this requirement which I had earlier on isomorphism that preserves algebraic subgroups is essential, right? We don't get it for free. And it's actually quite a strong requirement. Nevertheless, in the case of surfaces, we were able to prove that the image of most of algebraic subgroups is again an algebraic subgroup. More precisely, together with Alvaro Leyendo and Christian Urech, we prove that if x and y are affine surfaces, and there is an isomorphism from our x to our y of abstract groups, then the following is satisfied. If H is a connected non-unipotent algebraic subgroup of our x, then its image is again an algebraic subgroup of our y, isomorphic to H. Note that for unipotent algebraic subgroups, this is not true. If X is spherical G surface, then Y is also spherical G surface that is isomorphic to X. So this just determines a spherical affine surface by its automorphism group. So the main ingredient of the proof is the following statement.
Short question.
Assume S.
Sorry, short question. What is not true for unipotent groups? So what is broken?
So we have a counterexample. So what is not true? It's not true that the image of unipotent group is unipotent.
But it's algebraic in this counterexample, or it is not algebraic?
It's not algebraic. It's really nothing. So the statement which was a key to prove this theorem is the following. Let S be an affine irreducible algebraic surface and F be an automorphism or a birational transformation. Then the following two conditions are equivalent. There exists a natural K such that F power K is divisible. And divisible means you can take a root of your element of any order inside of the group, inside of out S or beer S, depends where your F lies. And second, F is algebraic. So the statement characterizes algebraicity in terms of abstract groups. And that's exactly what we want. Because if we have an isomorphism of abstract groups, then divisible element goes to a divisible element.
Once more, what is divisible? What is divisible?
So divisible means that you can take a root of any order inside of the group. For example, your element G in out S is called divisible if for any natural K, there is an element H such that H power K equals G.
Then I don't understand, why do we need this K here? Is it possible that F is not divisible, but F power K is divisible?
Yes, it's possible. For example, take GM and take a finite extension of GM. Any element inside of GM is divisible. But if you take an element, some element from GM times some element of finite order, not from the GM, then this element will not be divisible.
I see.
So basically, you take this power just to kill the finite order part, or how to say it, torsion part, so to say. Okay, so the proof of this statement is based on the dynamics of birational transformations of surfaces, and the proof works only in dimension 2. The reason why it doesn't extend to higher dimensions is that we know very little, I would even say essentially nothing, about dynamics of birational transformations in higher dimensions. Already in dimension 3, very little is known. But in dimension 2, we kind of know really a lot. Okay, so as you see, the theorem tells you very much in the case of surfaces. We proved something about toric surfaces, we proved something about Danilevsky surfaces, but using the theorem here, you can prove or characterize many other surfaces by their automorphic groups. And it would, of course, be nice to prove it for some other surfaces, let's say non-toric and non-Danilevsky surfaces, to prove something using this machinery which we developed. What about a higher dimensional case? So you see this approach, which I discussed, does not work in higher dimensional case. So here is the result together with Sashkanta and Junichi. So this paper just got accepted last week in the American Journal of Mathematics. So I had a lot of wines this weekend. Let the base field be uncountable algebraically closed field of any characteristic, also of positive characteristic. And let X be a connected affine variety such that the automorphic group of X is isomorphic to our AN as an abstract group. Then X is isomorphic to AN as a variety. So this basically says that X or AN is determined by its automorphic group, seen as an abstract group. This is actually maximum what we can get. If we try to extend this result to quasi-projective category, then it doesn't work because the automorphic group of AN is isomorphic to the automorphic group of AN times Z, whereas Z is projective with a trivial automorphic group, or even complete, if you like, with a trivial automorphic group. Moreover, the condition of connectedness on X is also important because the automorphic group of AN is isomorphic to the automorphic group of AN disjoint union with Z, whereas Z is an affine variety without non-trivial automorphisms.
And is there a counterexample for countable algebraically closed field?
So this is a good question. So the only thing which one could really weaken in this theorem is this uncountability. For example, can it be proved for Q for the rational numbers, or at least Q bar? Maybe even we don't need algebraically closed. So this is open. This I cannot tell you. So this is something what would be good to do, but it's not done yet. Yeah.
So the proof relies on this uncountability, right?
The proof relies on uncountability, yes. So the main ingredient, I will even tell you why. But now the main ingredient of the proof. Let X be an affine variety and V be an irreducible subvariety that consists of commuting elements. An identity element belongs to V. Then the group generated by V is an algebraic subgroup of our X. As a direct consequence, we have the following statement. Assume G is a commutative connected closed subgroup of our X, then G is a countable union of an increasing filtration by commutative connected algebraic subgroups of our X. So basically now, you see, if you have an isomorphism from our X to our Y, and X is toric, then X contains, for example, an algebraic subtorus. You can map your algebraic subtorus to our Y. It's a commutative, uncountable, closed subgroup I'll tell you a little later why it's closed. Then you can take a connected component of it. Connected component has a countable index. So the connected component is again a non-trivial subgroup. And then by this main ingredient theorem, you have that this connected component is actually a union of algebraic subgroups. So this theorem basically we use to reduce problems for infinite dimensional subgroups of out X to problems for algebraic subgroups. This proposition, or I should say this main ingredient theorem, does not hold for the group of birational transformations, unfortunately. Here is the example. Take X equals A2 and consider a subset in the group of birational transformations, so in this second Cremona group, of elements of the form xy is mapped to x comma 1 plus ax times y, where a is any complex number. So first, of course, identity is contained in V, because if a is equal to 0, then this is the identity transformation. But V is not an algebraic subgroup of the second Cremona because it's not of bounded degree. So if we'll iterate it n times this element for a non-zero, then the element will have degree exactly n. So it will go to infinity when we iterate to infinity.
And what is the inverse to this transformation?
What is the inverse? I don't know. I haven't thought about this, so I have to.
So this is an automorphism or not? So I try to understand.
It's not an automorphism of A2. So it's really a birational transformation. So you see, you have, for example, here like x, for example, comma xy, something like xy.
Mm-hmm.
I mean, no, not really, of course, because you have y plus axy. But okay, so this is not an automorphism, at least. This is something what can probably be even checked by taking Jacobian. Okay, so let me go further. So here is the main theorem which I want to discuss today. Let X and Y be irreducible normal affine varieties such that the automorphism groups out X and out Y are isomorphic as abstract groups. If X is toric and non-isomorphic to an algebraic torus, then varieties X and Y are isomorphic as varieties. So this really says that irreducible or just toric variety is determined by its automorphism group in the category of normal affine irreducible varieties, if this toric variety is different from algebraic torus. But in case it is algebraic torus, it is also determined by its automorphism group just in the category of affine varieties of dimension less or equal than dimension of the torus. So I will try to tell you some sketch of the proof of these two theorems. Of course, I will not go to the details because it's rather involved proofs, but I will certainly give you an idea how it works. So assume there is an isomorphism from out X to out Y, and T is a maximal subtorus, and U is a root subgroup with respect to T. X here is a toric variety. Y is any normal, irreducible affine variety. So the proof very roughly consists of 3 steps. So the first step is to prove that the image of algebraic torus is a subtorus of out Y of dimension dim T. And the image of a root subgroup is again a root subgroup with respect to the image of the maximal subtorus. The second step is to show the dimension of Y is actually dimension of X. And the last and most combinatorially involved part, the set of weights of root subgroups of out X with respect to T, and the set of weights of root subgroups of out Y with respect to phi of T coincide. So the third part is, of course, difficult, and I will not touch it. I will not touch it because actually I would need another talk or two to explain the third part. Centralizer lemma. Let X be a variety, an affine variety, and also irreducible affine variety. Assume G is a commutative algebraic subgroup that acts on X with an open orbit. Then the centralizer of G in out X is equal to G. Here is the proof. The proof is easy, so I will actually tell you it in details. Let H be an automorphism that commutes with each G from G. It should be here G. Oops. So it means that H is in the centralizer of G. By definition, there is an open dense G orbit in X. Let's say U. Since GU intersected with U is non-empty, so it's a non-empty open subset, there exists X in U such that HX belongs to U. Using that U is GX, we find some element G naught inside of G with HX equal G naught X. Thus, for each G inside of the group G, we get that HGX equals GHX, well, because H is in the centralizer of G. Further, it is equal to G naught X, well, because of this equality, HX coincides with G naught X. And now G is a commutative group, so it is equal to G naught GX. Using that U is dense in X, we get that H and G naught coincide on the dense open subset. So the action of H and G naught coincide on the dense open subset of X, and therefore they coincide on the closure, so on the whole X. So we get that H is equal to G naught, which belongs to G. Why is the centralizer lemma important? We'll take a maximal algebraic subtorus T in out X. It acts on X with an open orbit by definition, because X is toric. Therefore, T coincides with its centralizer. Hence, the image of T again coincides with its centralizer inside of out Y. And if some subgroup coincides with its centralizer, then this is a closed subgroup. This is not difficult to show. Now, by main ingredient theorem, the connected component of phi of T naught is a union of commutative connected algebraic subgroups GI. And of course, each commutative connected algebraic subgroup is isomorphic to the product of algebraic torus and some commutative unipotent group. This is true only over characteristic 0, of course. If we go to positive characteristic, then unipotent groups look much more complicated. Take a root subgroup U of our X with respect to T with the weight character mu. Then the subgroup char mu times U again coincides with its centralizer in our X, Y. Well, the kernel of mu is just a finite extension of n-1 dimensional torus. So you have here a product essentially of n-1 dimensional torus and a unipotent one-dimensional group. This group again acts with an open orbit on X. And by lemma we had before, this coincides with its centralizer. So this means that the image of ker mu times u is closed because it coincides with its centralizer. Using these two facts, one can prove that the image of a root subgroup is closed in our Y. To show that the image of a root subgroup is connected, we know that T acts transitively on U minus identity by conjugation. Hence, the image of a torus also acts transitively on the image of a root subgroup minus identity. Now, the connected component of phi of u minus identity is a subset of phi of u minus identity, of course, obviously. But this subset is left invariant under the phi of t action. Now, as phi of u is uncountable and phi of u naught has countable index in phi of u, it follows that the connected component is non-empty. Well, it's non-trivial, and the connected component minus identity is non-empty. And one can show here, well, it's really not difficult, maybe even easy for some of you and obvious, that phi of u naught minus identity y actually coincides with phi of u minus identity. Or in the other words, the image of a root subgroup is connected. So we proved first that the image of a root subgroup is closed, and now we prove that it's also connected. Since phi of u is closed and connected, by main ingredient theorem above, we have that phi of u is the union of connected commutative algebraic subgroups hk of our Y. Moreover, since phi of u does not contain elements of finite order, all these algebraic groups hk are actually unipotent. So there are no tori inside. Assume we have n root subgroups with respect to t. And this we can always assume, of course, because once we have one root subgroup, we have many of them. So assume these root subgroups have different weights, mu1, mu2, and so on, mu_n. One can prove that T yacht is, which is the intersection of all ker mu j except 1, or ker mu I, sorry, except 1, then this T yacht is a finite extension of one-dimensional algebraic torus. Now, phi of T yacht is a closed subgroup that acts on phi of u by conjugations. Well, why it's closed? Because it's inside of phi of t, and phi of t is closed. So phi of t yacht is just a subset of those elements of phi of t which commute with images of n-1 root subgroups. So that's basically the reason why it's closed. Now, by main ingredient theorem, we have that the connected component of phi of t yacht is the union of algebraic groups. Now, what are these algebraic groups? To figure this out, we note first that phi of t yacht naught acts on phi of u. Well, this is basically because t yacht acts on u, This implies that phi of t yacht acts on phi of u, and this implies that phi of t yacht not acts on phi of u. Now, both these groups are unions of algebraic groups. So they are nested in groups. This implies that GK acts on H, S, K, where S is some natural number which depends on K, for any natural K. Moreover, because T yacht acts on U with the finite kernel, GK also acts on HSK with the finite kernel. And using Lee-Colchin's theorem, one can prove that GK does not contain a copy of GA. Well, actually, if it would, then this GM would have a fixed point by Lee-Colchin's theorem. And then the kernel would be infinite, which is not possible by construction. So therefore, we have that phi of t yacht naught is actually an algebraic torus. So let me just ask you, do you still hear me? Because I don't see you, and I'm wondering if there is nothing wrong with the connection.
We hear you.
Okay.
Okay, very good. So basically, in using these tricks, we prove that phi of t yacht naught is an algebraic torus. Moreover, since phi of t yacht naught can be embedded as an abstract group into GM, by looking at torsion elements, we conclude that R is 1. So we conclude that the connected component of phi t yacht is just isomorphic to GM as an algebraic group. Moreover, one can show that phi of t yacht acts on phi of u with an open orbit, which implies that phi of u is also one-dimensional. And you remember phi of u was just a union of unimportant subgroups. So if it's one-dimensional, it has to be GA. So we proved now that root subgroup U is mapped to a GA, to a subgroup which is GA as an algebraic group. Now, to prove the dimension of phi of t naught is n, we remark that all phi of tj naught are positive dimensional algebraic tori. Well, they are just isomorphic to GM, as we just showed. And the homomorphism phi of t1 times and so on phi of tn to phi of t is surjective and has a finite kernel. Moreover, the image of rho is a countable index subgroup of phi of t naught, and in turn phi of t naught is a countable index subgroup of phi of t. To prove that phi of t coincides with phi of t naught is a little bit involved, but the main idea is to show that the connected component phi of t naught is just a finite index subgroup of phi of t, not a countable but finite index subgroup. And now, since both groups phi of t naught and phi of t are isomorphic as abstract groups to an algebraic n-dimensional torus, all elements of finite order of phi of t are already contained in phi of t naught. So therefore, this finite index subgroup should coincide with the whole group. So this proves that phi of t naught is equal to phi of t, or in the other words, algebraic torus is indeed sent to an algebraic torus. So let us summarize what we proved so far, or, well, proved without some details, of course. So algebraic torus goes to an algebraic torus of the same dimension, and a root subgroup goes to a root subgroup with respect to the image of the torus. So this is something really nice, and this is exactly the first step of the proof. The second step of the proof, you remember, is to show the dimension of y coincides with the dimension of x. Well, since phi of t is isomorphic to GMN, so it's an algebraic torus, we have the dimension of y is at least n. Now we like to show the dimension of y is less or equal than n. Phi of u is a root subgroup with respect to phi of t with some character weight xi. Hence, the image of ker mu, and note that ker mu is just a finite extension of n-1 dimensional torus. So the image of ker mu coincides with ker xi. And ker xi is again a finite extension of n-1 dimensional subtorus of phi of t. Denote by d the connected component of ker mu naught. In other words, d is an n-1 dimensional subtorus of out x. One can prove now that phi of d is also n-1 dimensional. Well, it's actually really not difficult to see even from this from this slide here. The ring of regular functions O of y, we can take all the invariants there under the action of phi of u. You remember phi of u is just GA. It's just a root subgroup. Now, d commutes with u, which means that phi of d commutes with phi of u. And this induces a natural action of phi of d on the invariants Oy phi of u. So we claim now that this ring of invariants is multiplicity free with respect to the natural phi of d action. If it's not the case, then we can form a generalized root subgroup with respect to d inside of our x of any natural dimension. And this is not possible. So this is something what is not possible. Again, it's something to prove that it's not possible, but it's, well, one can prove that. So now this invariant ring is multiplicity free phi d module. And phi of d, you remember, is n-1 dimensional subtorus of out y. This means that phi of d acts on y quotient by phi of u, y quotient by GA. And actually, in this case, this quotient is affine. It's not quasi-affine. So this invariant ring is finally generated. So we have n-1 dimensional torus that acts on the quotient of y by GA with a dense orbit. This means the dimension of y is less or equal than dimension of d plus 1, which is n. So we prove the inequality in another direction. Here we have the dimension of y is bigger or equal than n, and here we have the dimension of y is less or equal than n. We conclude the dimension of y is n, and hence y is toric. So now, of course, we have two toric varieties x and y. And as I told you before, to explain 3, one would probably need another 1 hour, so I omit it. So we prove that x and y are toric, and further by combinatorial tricks, one can prove that these two toric varieties are actually isomorphic. Now, I also promised you to give a sketch of the proof of theorem B. The main ingredient of this proof is the following corollary of a very deep result of Serge Cantin and Jun Ishii, which was recently proved in Acta Mathematica. Let gamma be a subgroup of a finite index of SLNZ, fine irreducible variety, such that gamma embeds into out Z. Then dimension of the variety Z is bigger or equals than n. So this is a little bit similar to in fact, this result, I don't state it fully, but it's a little bit similar to Margulis superrigidity theorem. It's just a far generalization of this Margulis superrigidity theorem, but very partial generalization, of course. Now, our X now, variety X, is just algebraic torus. So we have an isomorphism from out T to out Y, and this isomorphism is just an F group isomorphism. Again, a maximal subtorus T in out T is just its own centralizer. So it follows that the image of T is closed in out Y, similarly as in the proof of theorem A. By main ingredient theorem, there exists an increasing filtration by commutative algebraic subgroups G1, G2, and so on in out Y, such that phi of T naught is the union of GK. As GK is commutative, we get that GK is isomorphic again to a product of algebraic torus and a commutative unipotent group. By counting torsion elements, we conclude that Rk is always less than or equal to dimension of T for any k. And after discarding finally many of Gk, there exists a torus D in out Y with Gm Rk equal to D for all k bigger or equals than 1, for all k big enough, essentially. So this means, so we choose first an identification, T equals Gm power n. So T is just an n-dimensional algebraic torus. Then the while group Wt may be identified with GLN Z. So the group of automorphisms of T, where T is seen as an algebraic group. Using this identification, we may see SLN Z as a subgroup of out T. And this subgroup normalizes T. Hence, the image of SLN Z normalizes the connected component of phi of T, which is G. So G is the connected component of phi of T. So now we distinguish three cases depending on the dimension of algebraic torus D. The first case is dimension of D equal n. Well, in this case, because dimension of Y is less or equals than n, we have that Y is an affine n-dimensional toric variety. And now simply applying theorem A to the isomorphism phi power minus 1, we conclude that Y is isomorphic to T as a variety. So this is kind of a trivial case. So the second case is when dimension of D is strictly between 0 and n. As phi of SLNZ, so as the image of SLNZ normalizes G, and remember G is the connected component of the image of T, And since D is the subgroup of all semi-simple elements of G, the image of SLN Z, phi of SLN Z, normalizes D. Hence, the phi of SLN Z action by conjugation on D gives us a group homomorphism from phi SLN Z to the automorphous group of D, where D is seen as an algebraic group. So the automorphous group is simply GL dimension DZ. Now the subgroup Ker-N, the kernel of eta, is either finite or a finite index subgroup. It's simply because any normal subgroup of SLNZ is either finite or is a finite index subgroup. The case when kernel of eta is finite is not possible, simply because SLNZ cannot be embedded to GLKZ, where K is strictly smaller than N. This, for example, follows from Margulis superrigidity theorem. Therefore, we are left with the case the kernel of eta has a finite index in phi SLNZ. Well, in this case, the pre-image of the kernel of eta acts trivially on the pre-image of D, simply because the kernel of eta acts trivially on D. But this is not possible because the set of fixed points in T under the action of a finite index subgroup of SLNZ is just the identity. So in phi power minus 1 of D, the pre-image of D is uncountable subgroup of D. So this is again not possible. So we come to the third case, dimension of D equals 0, using that the quotient of the automorphous group of T by an algebraic torus T is just GLNZ. T has a countable index in the automorphous group of T. Hence, G has a countable index in the automorphous group of Y as well. And since n is bigger or equal than 1, G is uncountable. In particular, because dimension of D is 0, G is a union of commutative unipotent algebraic subgroups HK of our Y. So all these unipotent subgroups have the same invariance, because otherwise unipotent subgroups would not commute with each other. So therefore, the quotient of Y by G is a quasi-affine variety of dimension n-1, endowed with a non-trivial action of SLNZ, which is not possible by corollary from the theorem of Kantan-Chi. So this roughly ends the proof of theorem B. And as a consequence, we are done with the proof of theorem B and with the proof of theorem A. Now I would like just to tell you a few words about a possible future work. So the first point would be to show that an affine spherical variety is determined by its automorphous group, and possibly extended to further varieties, for example, to G varieties of complexity 1. This would probably be very difficult because we couldn't do it for spherical varieties, even if we have the isomorphism that preserves algebraic subgroups. So that is probably a tough problem, but it would be, of course, very nice to do it. And second is to find more applications of this main ingredient theorem. You remember this theorem about commutative connected subgroups of the automorphism group of X. I believe there should be many applications of this theorem. Maybe some are even easy. I can give you one very easy applications of this theorem. For example, take an affine variety X and assume that X admits no GA actions and no GM actions. Is it possible that the automorphism group of X is infinite dimensional? We don't know. So this is one of the open problems, and I believe one of the most important problems in the theory of the automorphism groups. So from this main ingredient theorem, we know now that if such group exists, if such automorphism group, which is infinite dimensional and contains no copies of GA and GM, then this automorphism group should not or cannot contain any uncountable commutative subgroup if we work over C. Because once it contains uncountable commutative subgroups, it immediately contains a copy of GA or GM. So yeah, this is just one small remark. And I thank you for your attention, and I'm very happy to answer any questions. Well, at least if I can answer them.
Thank you, Andriy, very much. So, who would like to ask or to comment the talk?
I have a couple of questions. One is a general one, there's several about proof. First, at some point you saying that if you have an automorphism group of variety X, it can be isomorphic to automorphism groups of at most finite number of spherical varieties,
yes.
right?
Mm-hmm.
So if you try to characterize spherical varieties by their automorphism groups and put them in baskets with the same automorphism group, then the equivalence class of spherical varieties with the same automorphism group is at most finite, right?
Yes.
So it's possible to, so probably, what is the abstraction to characterize completely or to the spherical varieties, or to give an example of such an equivalence class?
Well, it's a good question, but
So,
you see, I mean, for affine spherical varieties, there are two combinatorial, like two most important combinatorial data. One is weight monoid, and another one is a so-called spherical roots. So we prove that weight monoids coincide for these two varieties. If one can prove that also spherical roots coincide, then this would solve the problem entirely. But we just couldn't do it. So of course, yeah. Go on.
I'm sorry. So for a given weight monoid, you have only a finite number of spherical varieties, finite number of choices of roots, right?
Yes.
Of colors.
Of spherical roots. Yeah. Mm-hmm.
Yeah. So did you try some examples?
Well, okay. I mean, you can take easily two affine surfaces which have the same weight monoid, and there are such. For example, you can take SL2 quotient by a torus and another one quotient of A2 by a cyclic group of order 2. They have the same weight monoids with respect to SL2 action. But you see, in this case, it's trivial because one is toric, one is not. So of course, we tried some examples, but we never found a counterexample. It seems there is some idea now which can partially solve this problem, at least for like SLN, spherical SLN varieties, for example. But I didn't check the details yet. But anyhow, so we don't have a proof for a general case. Maybe for some varieties like SLN C, it could work. But in general, life is kind of complicated, and I would like to prove that spherical roots coincide, and I feel it should be possible, but I don't know how.
Thank you.
Okay, dear colleagues, any more questions, comments?
Well, I have two small questions which might be not quite interesting about the proof, if you allow it.
Please, sure.
Okay, Andriy. If you go to 2 pages before, oh, okay. So here you have unions of commutative algebraic important subgroups, and you say that they should have the same invariance, otherwise they would not commute each other.
Yeah.
But let's take a picture as follows. We take an A2, a two-dimensional commutative unipotent subgroup, which acts with two-dimensional orbits, and you take different one-dimensional subgroups in there. They commute, they have different invariance, but what breaks? Why this example is not possible?
Well, so you take essentially a two-dimensional unipotent group which acts with a two-dimensional orbit, right?
Yeah, let us say that maybe it does not exist, but several unipotent one-dimensional subgroups from there exist.
Okay, so it's so in this case it's easy. Especially it should be easy for you because one of the possible arguments could be our paper with you. So you see, this G is a union of commutative unipotent algebraic subgroups. This G contains all algebraic subgroups, all algebraic subgroups of out Y.
I see.
So that's the point.
Okay.
If you have some which have different invariants, then you can take replicas and take those which do not commute.
Yeah, and replicas, they always exist. Here.
Yeah.
Okay. Okay, and then I have another small question.
Yeah.
If you go back 2 pages, I guess, maybe, yeah, here, you say that the subgroup of the automorphism group of the torus of out T normalizes the torus. But I don't understand what does it mean here and normalizes, because it acts on the torus essentially.
Yes, it acts on the torus, so it normalizes the torus. I mean, essentially, it's more or less by definition, right? If it acts on the torus, it means it normalizes the torus.
It's just a tautology. Okay, thank you.
Yes.
Okay, if we have no more questions, then I have a general question concerning these activities with the study of varieties by the properties of the automorphism group. Theoretically, there may be 2 points of view. First point, this is really an important question, whether the automorphism group characterize a given variety. This may find some applications in some study of geometrical algebraic properties, or this is a question of fundamental structure of nature and so on. Another point of view. This is just a motivating question. So we don't expect any applications or don't consider this as a fundamental feature, but this is a motivation for us to study automorphism group. And in the process of proving such theorem, we found many important features, interesting properties of the automorphism group, their maps, and so on. So what is your point of view to this subject?
So my point of view are both. So it is okay. So it's hard to say if something is important or not. So it's just kind of like it's beautiful or not. It's attractive or not. So this is just concerning your first question.
Okay,
I would say that the question itself.
But the question concerning applications, this is quite concrete question. Do you have?
Yeah. This is true. This is true. But first, I'm answering the first one, or argue about the first one. So I would say that this question is natural. As I said, it strongly relates to this Erlangen program, and well. It's just beautiful from my point of view. So now concerning the second point, I like the point of view of Serge Quentin. So we prove theorems not to prove results, but to develop the technique which help us to prove the results. For example, in order to prove the theorems, we prove this main ingredient theorem, which most probably will have many applications, not only for our question, but also for many other questions. Proving this results, we proved this a lot of results about surfaces. Really, a lot of results about surfaces. Also, this divisibility equivalent to algebraicity. For example, we proved many things about the centralizer of some subgroups. For example, centralizer of a GM action inside of the automorphism group of a surface, and so on and so forth. So I don't like many combinatorial things about spherical varieties. So it's essentially important from my point of view, because mathematics is a language. What we do in mathematics, we develop the language. And from this point of view, it's important, it's less important to prove results, but actually to develop the tool. So to develop the language. I'm done.
Okay, I see. Thank you for your comment. So dear colleagues, if you don't have any more questions or remarks, then I would like to thank Andriy for his nice talk. Thank you very much.
Okay, thank you. Thank you for the invitation. And